Hey everyone, and this is homework 3.11. Sorry about any background noise. I am recording this at home today, so you might hear some of my family. All right, so today we looked a little bit more at some of our exponential functions, and this first one is an example of a test problem. So I'm going to show you. If you were to see an equation and then be asked to match a graph, well, we have our starting value at 4, which means when x is 0, then y equals 4. So we need to look for a point on the graph that shows us 0, 4. And so easily that helps us to eliminate the second one here because this has a y-intercept of 2. We can also look at the type of equation it is, and in this case, this exponential value is a decay value. It's going down because we're multiplying by 1/2. So we should see a line that is going down or decreasing. The only one that remains that is doing so is this one right here. It crosses at the 4, which is great, and then it is going down, so it is a decay function. All right, let's look at lesson 11 practice problems. Oh, excuse my earlier markings here. All right, so this is showing that someone who's measuring a ball that is bouncing and it's come back up. And then it is now, let's go ahead and use this ruler here. It is now at this height. And it says it wants to measure the top of the ball. And so this would be the top of the ball here. And so if I'm measuring the top of the ball, go ahead and grab my pen. Right, and I'm using this ruler here to see kind of where that would be. The top of the ball is resting around this point here. And so we have 26, and then this would be 26.5 here. And so the line before that, that hashtag, this is also a measurement practice, would be 26.4. And it looks pretty much exactly on the line, so we wouldn't need to worry about 0.43 or 0.431. All right. Function h describes the height of the ball in inches after n bounces and is defined by this equation. What is h of 3 and what does it represent in this situation? So if we were to plug 3 in here, we would have 120 times 4/5 to the power of 3. So let's go ahead and do 120 times 4/5 to the power of 3. And we get 61.44. And this means after 3 bounces, the ball is 61.44 inches. It says, could h of n be 150? So could the height of the ball be 150? No, we know that the starting height was 120. So the starting height is 120 inches. So it doesn't make sense that it would be 150 inches unless for some reason before we started measuring the height of the ball, it was dropped from a higher point. But that seems unlikely. So which ball loses its height more quickly, the ball or a tennis ball, whose height in inches after n bounces is modeled by this function? So in this function, the factor is 5/9. So that's the remaining height, right? That's its bounce factor versus a bounce factor of 4/5. Well, you should hopefully recognize that 5/9 is a smaller fraction than 4/5. But if you don't, you can do 4/5 gives us 0.8. That's 80% rebound. And then 5/9 gives us 55% rebound. So function f loses height more quickly because it retains less of its bounce. It says, after how many bounces would it take for the ball to be less than 12 inches from the surface? So let's use our graphing calculator for this. We're going to do 120 times 4/5 to the power of x and graph that. And it's not showing up, so let's zoom out a little bit. There we go, now we can see it. And then I'm going to go to second table, and I want to look for where my height is less than 12 inches. And so that happens at 11 bounces, because at 11 bounces it is, looks like 10.308. So sometime after 10 bounces, right, it's going to be losing that rebound quality and bouncing only back to about 10.3 at the 11th bounce. All right, so after its second bounce, a ball reaches a height of 80 centimeters. So we have a ball bouncing and coming back up, and it's hitting 80 centimeters. The rebound factor from the ball was 0.7. From approximately what height was the ball dropped? So we know in this case it has to be greater than 80 because the ball was dropped from a higher height. And so it's either 115 or 163. Well, our rebound factor is 0.7, which means we're multiplying the original height times 0.7 to get to 80 centimeters. So if we do 80 divided by 0.7, that's going to give us 114.2. So if we're thinking about approximately what height, it would be 115 would be our closest value. All right, which equation is the most appropriate for modeling this data? So here we have our inputs at the top. So this is just using, sometimes it's confusing when they shift the graph to be horizontal. So if you're struggling with that, just go ahead and rewrite it. But here we are looking at whether or not this is an exponential equation or not. So it goes from 79 to 101. And so that means that this is exponential because 101 minus 79 is 22. That's not going to be 1.25x. And then if we do 124 minus 101, we get a difference of 23. 158 minus 124, we get a difference of 34. So notice that each time, if we let's check the next one, 195 minus 158, we are getting a different number difference here. 244, that's going to be a much bigger one. 195 is 49, right? And so this is probably more logically going to be represented by a exponential function. So we can easily eliminate C and D. And then the question is, right, if we were to go 101 divided by 79, we get 1.27. Okay, 124 divided by 101, just to check, 1.22. So they're all looking at about between 1.22 and 1.27. So 1.25 looks like a good factor. Now 79 is the first term, not the original term. So it can't be that, it would have to be A. And we can double check this by saying, well, if we were to take 79 and divide by 1.25, we get 63.2. So that's going to be close enough to getting this one right here. Okay, and again, that original value is not the same as the first value, and so it would need to be not 79, but 64. Number 5, the table shows the number of employees and number of active customer accounts for some different marketing companies. Would a linear or exponential model for the relationship between the number of employees and the number of customers be more appropriate? Well, let's see. Here we're doing +4, +5, +4. Now here we're skipping to the number of employees being 10. So we do need to be a little bit careful with that. If we were to do a factor here, we would do times 2, and then 13 divided by 8. Oops. 13 divided by 8 gives us this would be times 1.6. And then we would be doing 17 divided by 13, which is going to give us 1.3. And then, so each time these factors are pretty different versus our addition actually seems to be pretty constant. If we were to keep adding by, let's say, 4 or 5, we would get then, right, if we continue this, 5, 6, 7, 8, we would get, let's say we add 5, we would get 22, 27, 32, 37, right? So this is going up by 5. Maybe that was a little too large. But if we go up by 4s, let's see what happens. So we get 17, we would get 21, 25, 29, 30, 3, 9 would be 37, 10 would be 41. So this doesn't seem to be a exponential relationship. It seems to be a little bit more linear because the difference is more consistent than the factor, right? So each time we'd be multiplying by a different number. If we were to estimate this, right, before, then maybe it would be like 2 to the second, or even let's do 1.6 power, right? So to the 10th power, you would get 219. You would get a much bigger number than 39 at the 10th value. So this generally seems to be looking a little bit more linear. All right, number 6, a bank account has a balance of $1,000. It grows by a factor of 1.04 each year. Explain why the balance in dollars is a function f of the number of years since the bank account was opened. So this is for every year there is one amount as an output. So for every input, there is only one possible output. We can't say, oh, after 10 years, there's $1,100 and $2,000, right? There would be one single amount. And then if we write our equation, our starting amount is $1,000 times 1.04, which is our factor to the power of time. And if we want to write that fully in function notation, we can include f of t. The table shows the number of people n who went to see a musical on the 10th day of April. What is the average rate of change for the number of people from day 1 to day 7? So day 1 to day 7, we're going to do 7 minus 1. And then we're going to do our output, 1720 minus 1534. So 1720 minus 1534 divided by 6 is going to be 31. So this would say that each day the number of people increased by 31. However, if we look at this first jump here, 2,324 minus 1534, we get 790 here, right? So this is an increase of 790. So this is not a good measure. Also because notice, excuse me, I spelled measure wrong. Notice that we are generally increasing by a lot, and then all of a sudden we decrease between weeks or days 6 and 7. So you could also mention that this is not a good measure because it increases by a lot until day 6, and then we see a decrease. All right, number 8 is practicing piecewise function reading. So this graph shows the cost of dollars of mailing a letter. So this is the weight, this is the cost of that letter. So how much does it cost to send a letter that weighs 1.5 ounces? That would be about here. So that's 1.15, $1.15. 2 ounces would be here. That is still $1.15 because this circle is filled in. If we were to be talking about 2.1, then we're going to be up here at that next amount. It says, what is the range of this function? So the range is the possible outputs. So the possible outputs are $1.15, $1.61, and $2.08. Those are the possible outputs that we could have. You could say between $1.15 and $2.08, but there are 3 specific possible y values that we have. All right, that is it for your homework. Today's code word is Mentos. Mentos, you know, that lovely gum. Make sure to put that at the top of your classwork paper in the appropriate spot here. And if you have any questions or you need any help with anything, please let me know. Happy homeworking and see you tomorrow.